Well, hello again. I know I've said this before, but I think I fixed the audio issue with this microphone and Zoom. You know how it cuts in and out? I listened to portions of the videos that I've put up, and it's super annoying. I'm sorry about that. If this doesn't work, this fix that I stumbled upon, then my next solution is to just take a baseball bat to the whole thing. So that ought to work. Okay, in the previous video about the fundamental theorem of calculus, I emphasized the relationship between these two functions, which I called big F and little f, in keeping with what a lot of textbooks do. So little f is this function enclosing some area. Big F is the formula for the area. And we found that if the derivative of big F is little f, then, well, this is just a restatement of that same thing. Let's put it this way. If the derivative of big F is little f, then the integral of little f is big F. This quantity right here actually is big F. It's the area under the curve f of t from a to x. Now, we're not talking about these arbitrarily named functions, big F and little f, so much in physics. We're talking about position, velocity, and acceleration. So to begin with, let's review the relation between acceleration and velocity. If we have a graph of velocity versus time, so here's a velocity that's decreasing, increasing, decreasing, the velocity is changing in time, that means there is an acceleration. Well, we can draw a secant line between 2 points on the curve, calculate the slope of the secant line, that would be the change in velocity over the change in time, that's rise over run. That's what we call average velocity. If we take the limit for shorter and shorter time intervals, this secant line approaches the tangent line, and the slope of the tangent line, instead of calling it delta v over delta t, we give it the special name dv dt. In other words, the derivative of velocity with respect to time. So acceleration is the time derivative of velocity, and that means the acceleration is the slope of the tangent line on a graph of v versus t. So let's connect this with everything we just reviewed in calculus. There we had a function big F whose derivative is f, little f. And there we were differentiating with respect to position. You can think of this as our independent variable. Often in calculus, x is your favorite go-to independent variable. And we could say that capital F was an antiderivative of lowercase f. In that, same statement over here. This is big F, right? The area under f of t from some left endpoint to a variable x, the variable right endpoint, that is the area function. That's what I was calling capital F. The derivative of that area function gives you little f. Let's just make a direct connection here. In this instance, we're differentiating not big F, we're differentiating a function that we call velocity. It is a function because it's a quantity that depends on time. And instead of taking the derivative with respect to some variable x, almost always in this physics class, we're taking derivatives with respect to time because we're talking about motion. Motion involves rates of change of position, rates of change of your velocity, etc. So the derivative of velocity is acceleration. Another way of saying that is that velocity is an antiderivative of acceleration. And all you have to do is match those quantities up with the analogous quantities in the general calculus discussion, and you can see that if velocity is if acceleration is the derivative of velocity, then velocity should be the integral of acceleration. It probably seems like we're going around in circles here, but here we're taking a derivative with respect to time. Notice how time is in the upper limit. And here's something I didn't really emphasize in the last video. When you're presented with the fundamental theorem of calculus in math class, often it's pointed out that if you're taking the derivative with respect to x of all of this garbage where x is the upper limit, then you just have to evaluate the inside function at x, and that's true. In this case, the variables are different. We're differentiating with respect to time here, so time needs to be that variable in the upper limit. You can't have the same symbol here and here. This is called a dummy variable. After you've done the integration, that variable goes away. So that's why I've had to go with t prime instead. So you all know from calculus that this means the area under the acceleration curve between these two times. It's an area under this curve. And we're taking the time derivative of that area. So this equation says that acceleration is the time derivative of all of this junk. Well, we know that acceleration is the time derivative of velocity. So this quantity must be velocity. Acceleration is the instantaneous rate of change of velocity, hence all of this junk must be velocity. In other words, velocity is the area under the acceleration curve. And this is kind of a subtlety, but really it's change in velocity. That's the area under the acceleration curve. And that will be clearer in a moment. But I'll say that right now, that it's delta v, the change in velocity, which is numerically equal to the area under the acceleration curve. So this is really the result that will help us see that more clearly. This is what you're going to use most often. This was the part 2 of the Fundamental Theorem of Calculus. If you happen to know an antiderivative of little f, any function big F whose derivative is little f, that's called an antiderivative. In the previous video, I looked at capital F, capital G. Those were just areas starting from different left endpoints. If you want to integrate or find the integral of little f between these two endpoints, take any antiderivative. Doesn't matter if it's big F, big G from the last video. Any function whose derivative is little f is called an antiderivative, and evaluate that antiderivative at the two endpoints and subtract. You've done this many times in calculus, but that is probably the more useful form of the Fundamental Theorem of Calculus for our purposes here in this physics class. In order to calculate this integral between a and b, find any antiderivative and evaluate it at the two endpoints and subtract. Well, how do we connect that to what we're doing here? Well, before we get to that, Grant Sanderson, the guy who does the 3 blue, 1 brown channel, he had a nice graphic basically saying this. You take the antiderivative of little f, which is like integrating to get big F, take the derivative of big F to get back to little f. Hopefully that helps you organize your thinking, because I know there's a lot of sentences being thrown around here, a lot of relationships. It seems like we're going around in circles. So I've minimized the previous slide up here, and let's make a direct connection to what we're talking about now. Instead of calling this function here f of little f of t, pretend it's the acceleration versus time function. This is how, suppose, acceleration depends on time. And my endpoints, instead of labeling them A and B, let's go with t initial and t final, because that's often how we describe the time interval in this class. We know that the derivative of velocity is acceleration. Now we're talking about a time derivative, not a derivative with respect to this arbitrarily named variable x. So you could say that acceleration is the time derivative of velocity, or you could say that velocity is an antiderivative of acceleration, same thing. And that means that if we want to integrate acceleration between these two times, using the Fundamental Theorem of Calculus, part 2, as it's often called, in order to find the integral of acceleration between these two times, just take any antiderivative, namely velocity, evaluate it at those two times, and subtract. Just what you've been doing in calculus, but now you're doing it with the vocabulary of kinematics, these kinematical quantities, position, velocity, acceleration. And that's really the key result. So I'm putting a big special red box around that. You need to memorize this. At the very least, have it in your notes or have it accessible, but it's best to just memorize it. The derivative of velocity is acceleration. That's easy to remember because we know that acceleration is any change in velocity. If you're accelerating, it's because your velocity is changing. And this says that the, I could word it as the integral of acceleration between t initial and t final, but graphically we can say the area under the a of t curve is the change in velocity. Velocity at time final minus velocity at time initial. Now, this notation is a little excessive. We could have just put v sub f for v final. That's the same thing as the velocity at time final. So again, v final minus v initial, that works just as well. But in words, the area under the acceleration versus time curve equals the change in velocity. It looks like nothing's changed here, but it has. Take a careful look here. Now I've switched to the relation between v and x. Here's the previous slide. This is the relation between acceleration and velocity. Now we're looking at the relationship between velocity and position. So it's a little lazy that I didn't change the graph here, but let's just now pretend that this function is how velocity depends on time. Excuse me. So velocity is the time derivative. It's the rate of change of position. That's equivalent to saying that position is an antiderivative of velocity. And if that's true, then the fundamental theorem of calculus tells us that if you would like to integrate velocity between two times, just take the antiderivative or unantiderivative of velocity, which is position, evaluate it at those two endpoints, and subtract. Same thing we did before, but instead of now talking about the area under the acceleration curve, we're talking about the area under the velocity curve. And instead of the change in velocity, we're talking about the change in position. You really don't have that much to memorize. It's like we're making an integral statement over here, and we're making a differential statement over here. You don't have to memorize both of these. If you can just memorize the two derivatives, namely acceleration is the rate of change of velocity, and velocity is the rate of change of position, if you can just memorize those two derivatives and understand the fundamental theorem of calculus, just really understand it in your bones, so it's intuition, then this stuff you already know anyway. It's not like something you have to memorize, it's just something you understand. And that would be the goal here. You're learning a lot in a short amount of time, but if you can get to that point, you've made it as far as kinematics goes. So I'll put a box around that too. The area under the velocity curve between two times is equal to the change in position. I could have called this x final minus x initial. Now there's another way to get to this result formally, and we should go through that, but it's worth repeating. The change in velocity is the area beneath the curve. Specifically, the change in velocity between two specific times is the area under the acceleration curve between those two times. See how these times match these times? That's important. We can make the same statement for the relationship between position and velocity. Of course, here we have a name, right? The change in position has a name. We call that displacement. So the displacement between any two times, I'm calling them t initial and t final. You could call them anything, or they could be any two times. The displacement between those times has the numerical value of the velocity, the area under the velocity curve between those two times. Okay, now procedurally, this is how you probably want to proceed. Is that redundant? Allow myself to introduce myself. You may, on your first exam, you may see a non-constant acceleration problem. Those do get covered in your book. There's a discussion of that in your chapter, and I'll do an example of that later in this video. And here's how you would start. I like to just start with the differential statement. Remind yourself that the time derivative of velocity is acceleration. And then we do something that physicists like to do. If you take a more advanced calculus class, there's a tendency not to regard the derivative as a fraction. You know, it's really an operator doing something to a function, but for many applications, it's perfectly valid and productive to treat a derivative like a fraction. This is a change in velocity divided by a change in time. So let's do some algebraic manipulation here. Put the t on the other side. And when you see something like this, after you've read some physics books for a while, you definitely get the itch to integrate. You see those differentials hanging out on both sides? Got to integrate. So we'll stick some worms in there. Now, this is not yet a definite integral because I have not specified my limits of acceleration. Here's how it works. Since we're integrating with respect to time, t is the integration variable, these limits need to be times. So I want to integrate from time initial to time final, as I've done here. But over here, I'm integrating with respect to velocity. So my limits of integration should be velocities, not times. And notice how my first limit of integration is v initial. That's the velocity that occurs at time t initial. That's very important. This limit corresponds to this limit, and the upper limit for the velocity integral corresponds to the upper limit for the time interval, or time integral. Okay, and then from here, usually it's just a math problem, and you can just use what you learned in calculus. This one's really easy. What's the antiderivative of, what are we actually integrating here? If you think about it, this is the integral of 1 with respect to v. There's an invisible 1 there. And the integral of 1 with respect to v is v. You know, just for calculus, it's like saying, what's the integral of dx? Well, that's x. Okay, so the integral of dv is v, and we have to evaluate at the upper limit, evaluate at the lower limit, and subtract. Now, the right side, I'm not going to do anything with. Just leave it as is, because in this discussion, I have not specified how the acceleration depends on time. So this is some function of t. What if it was t squared? Could you integrate that? No problem. That would be 1/3 t cubed. What if this was the cosine of t? Could you integrate that? No problem. Sine of t. What if it was e to the t? Yes, you can integrate that too. So as long as the acceleration is some function that you know how to integrate, you know, for which you can find an antiderivative, then you can finish this problem. But I'll just rewrite this finally like this. So I've recovered the result that I was already discussing earlier in the video. This says that the change in velocity between two times is numerically equal to the area under the acceleration versus time curve between those same two times. Change in velocity is the area under the acceleration curve. Let's repeat this procedure now. Yeah, so these are the same. Let's repeat this procedure with position and velocity now. So what I've done here is integrate once. I started with acceleration, I integrated once. Let's now integrate a second time, because presumably this first integration would tell us how velocity depends on time. Okay, we've seen this statement before, but I like to go about it this way. Presumably we know velocity now. We know how it depends on time because we did that first integral. We also know that position, or the time derivative of position, by definition, is velocity. So just like before, let's regard this derivative as a fraction. We'll move the dt over. Got that itch again. Let's integrate both sides. Over here, we're integrating with respect to time, so the limits of integration will be times. Over here, we're integrating with respect to position, so the limits of integration will be positions. Now, you could call these limits anything you want. You could call it t0 and t1, or t6 and t9. Doesn't matter. Here I've gone with t initial and t final, and that means that my limits of integration over here should correspond. If this is t initial, this would be the position at t initial. In other words, x initial. So x initial is the same thing as x evaluated at t initial. Well, what's the antiderivative here? The integral of dx is just x. What happened to my... Okay, it's just x evaluate at the upper and lower limits. Of course, x final minus x initial is what we call displacement. I'll just write it this way. So it looks like I'm kind of mixing up my notation here. X initial is the same thing as x evaluated at t initial. This is just a more succinct way of writing it, and that's usually how it's done in the physics books. Okay, so displacement is the area under the velocity versus time curve. Same result that we had up there. Now that we've developed that machinery, we can re-derive our constant acceleration kinematic equations using calculus this time, which is a more general approach. A few videos back, we developed those equations just by using some common sense reasoning. You know, the cat falling off the top of the building. We reasoned how the cat's velocity would depend on time because of its acceleration. We talked about average acceleration being, you know, halfway between initial and final. Here, we don't have to use our brains really. We just apply the calculus. So I will adapt the notation slightly. Let t initial equal 0 seconds. So my initial time when I do these integrals is just the number 0. And then our final time, we will relabel it simply t. And you're going to see that that's a little faux pas because we're going to use the same variable in the upper limit of our integrals that we use in the integrand. And that's a big no-no in math, but we're kind of sloppy in these physics classes. Don't blame me. Everybody does it, okay? I'm just trying to fit in. So like I mentioned a moment ago, I like to start from this statement. Oh, for now, yeah, let's assume that acceleration as a function of time is just a, which is a constant. Again, we're talking right now about constant acceleration. So usually when you see this letter a, it could depend on time. It could be a function of time, like t squared or sine of t. Right now we're emphasizing that it's just a number. In fact, if this were the gravitational acceleration, this number would be 9.8 or negative 9.8. So I'll start with this statement, that the time derivative of velocity is acceleration. If you can just remember that starting point, you may remember the rest of the steps. We like to move the dt over to the other side. So an infinitesimal change in velocity is acceleration times an infinitesimal change in time. And our next step is to draw our worms, as I heard a professor say a long time ago. And let's choose our limits. We're going to integrate from the initial time to the final time, which is from 0 seconds to our final time, which is just called t. So this is the part that's a little sloppy. You're not really supposed to use the same variable here that you would use here. In a math book, they might put a t squiggle. I did a t prime in the PowerPoint slides, but it's understood this is our dummy variable for integration, and then we'll plug in, when we evaluate the limits, we'll plug in a specific time t. So this represents a variable final time. Over here, the limits would be velocity at the initial time. Now, since our initial time is 0, then I'm going to call the initial velocity v sub 0. So this is the velocity at the initial time. You know, I probably should have even done this. Let t initial go to t naught, or t0, and call that 0 seconds. Because remember, t0 doesn't have to be 0 seconds. This is just a label. It's an index for your initial time. And since we're letting the letter t do double duty here, by the same token, we will let the letter v do double duty here. Yeah, the final velocity I will just call v, even though I'm also using the letter v as my integration variable. So this is common practice. The antiderivative of dv, or the integral of dv, is just v, evaluated at our upper and lower limits. Now what can we do here? A is a constant, right? Which means we can pull it out of the integral. You all know that. A constant can be brought out front, and then I would be integrating just dt. Well, what's the integral of dt? That's t. We're really integrating the function 1 with respect to time. Okay. And now this is looking really simple. Plug in v for v. Again, it seems redundant. We're plugging in these limits to the function. So this gives us v minus v naught on the left side. And on the right side, we'd have t minus 0. In other words, the velocity as a function of time is just, oh, I'm sorry, I forgot the, don't I have an a out front? That's no good. Yeah. I forgot to bring this a down. See, I've already pulled a out front, then I do the integral. Okay, so this is a times t minus 0. And here it is, v equals v naught plus a t. I've put the v naught on the other side. This is how the kinematic equation relating velocity and acceleration in time is often written, specifically constant acceleration. Remember, the way we've been using it is delta v equals a delta t. This is honestly a more correct way to write it. This equation says the same thing. In fact, you can see that here. This says change in velocity is acceleration times change in time, or time interval, because the final time is t and the initial time is 0. But commonly, the equation gets implemented in this form, where it's understood that this t is really a time interval. It's how much time has passed since time 0. And this was the velocity at time 0. So it's the same equation, slightly different notation. Honestly, the way your book insists on doing it, it's probably better, it's clearer. This has its advantages. In fact, it has its advantage right now because we're going to plug that into the next integral. So we've integrated once. Now we know how the velocity depends on time for this constant acceleration. The next step is to figure out how the position depends on time. So now I start with this statement. The time derivative of position is velocity. Now we know how the velocity depends on time. So we can integrate once again to figure out how the position depends on time. And maybe you just want to scribble this out and put the dt over here. I'll rewrite it. Dx equals v dt. Notice how I left space here because I knew I was going to write an integral symbol. Our limits of integration could really be any two times, but let's go with specifically time 0 and a final time t. The reason I'm choosing the limits this way is so that we find an expression like this. Instead of having delta t's running around, we've just got t's. Now, the limits on the position have to match the limits on the time. So the most natural name for the position at time 0 is initial position, and the most natural name for the final position at time t is just x. Again, that's faux pas. We're not really supposed to be using the same variable here. What's the antiderivative? The integral of dx is just x, evaluated at upper and lower limits. Now here is where we actually plug in our previous result. Aha! V is not a constant. We can't just pull that out. V does depend on time. You can see right here that as the time goes on, the speed changes, or the velocity changes, I should say. So we're really integrating v naught plus at, the quantity v naught plus at, with respect to time. This whole thing must be integrated with respect to time, but now this is a calculus problem. You know how to do that. Let me rewrite this as x minus x naught. Now, okay, I was going to skip a step, but let's do the whole thing. This is a constant, right? V naught is some number. It specifies the velocity at time 0. It's not a variable. So, just like before, if it's a constant, you can pull it out front, or hopefully you remember from calculus something like this. What is the integral of 3 dx? Well, that's just 3x, right? We're doing the same type of thing now, but with dt instead of dx. So this is v naught t. The first term, when integrated, gives us v naught t. And then we're integrating at. A is still a constant. What's the antiderivative of t? That would be t squared over 2. You raise the power from 1 to 2, and then you divide by that new power. It's the power rule for integrals. So 1/2 a t squared evaluated at 0 and t. Now, I'll point this out. Anytime you're integrating a polynomial, notice how there's no e to the t's, there's no sines of t, cosines of t, it's just powers of time. When you integrate a polynomial, you get another polynomial where the lowest power is t to the first. See how there's no constant here? So when you plug in your 0, all of those terms just go to 0 because they all have t in them, and t, 0 to any power is still 0, except for the 0 power. But like I said, there's no constants. Okay, so you don't really have to worry about what comes out when you evaluate at the lower limit if your function is, the function that comes out of the integral is a polynomial. So I know this seems a little circular because now I'm plugging t in for t, and it looks exactly like it does inside the brackets. Nothing's really changed. That's one reason not to be sloppy with the use of t. In a math class they wouldn't do this. Okay, this looks familiar, right? This says total displacement is speed times time. This is what you knew in high school. If you drive at 65 miles an hour for two hours, you went 130 miles. But now we can account for an additional contribution to the displacement if you are accelerating at a constant rate. Remember, this only works for constant acceleration. So you could write it like this, or it's kind of nice to put the x naught on the other side, and you could say this instead. When you write it this way, it kind of emphasizes that position is a function of time. So given the particle or car's constant acceleration and its initial velocity and its initial position, you can plug in any time and calculate where the particle is at that time. That's what the kinematic equation tells you. You need two initial conditions. You have to know what its velocity was at time zero, and you have to know what its position was at time zero. If you have those two pieces of information, and, well, one other thing, you need to know its constant acceleration throughout the motion. If you have those three pieces of information, two of which are called initial conditions, then you can calculate the particle's position at any time. We've already used this equation, right? Previously we said displacement is v naught times time interval plus 1/2 a delta t squared. This is the same equation as this one. The reason for the difference in appearance is right now our time interval is final time minus initial time, where the initial time is 0. So delta t just becomes the letter t. But it's really the same equation as the one that I just got by integrating twice. So the short answer, how do you get the kinematic equation for position versus time given the acceleration? You merely integrate twice. You integrate once to get velocity, and then you plug that into your next integral. And here's me integrating once to get velocity, then you plug the velocity function into your next integral to get position as a function of time. Okay, we don't need to do an example of that because you've already seen some examples of the use of that equation. Let's look now at what one would do if the acceleration were non-constant. So here's your one example of finding position versus time for non-constant acceleration. Kinematic equation for non-constant. And like I said, you should be able to find a couple examples in your homework as well and in the chapter. Okay. So instead of a constant number like 9.8, let's pretend that the acceleration of it could be a car, again, maybe a car, the light turns green, you step on the gas, but you don't push on the gas pedal with constant force. Maybe you step on it gradually, and then as soon as you see there's no cops around, you slam on the gas pedal. So maybe your acceleration looks something like, how about it's just 2t, 2t to the first power. That's a linear dependence, right? If you were to graph the acceleration versus time, it would just be a straight line with a slope of 2. So this is not a v versus t graph with constant slope. This is an acceleration versus t graph. This would be like I said, if you started out gradually pushing on the gas pedal and then you kept pushing harder and harder. So when you say a Porsche goes from 0 to 60 in 5 seconds, that's like saying 12 miles per hour per second. This is not accelerating at a constant 12 miles per hour per second. The rate at which you're picking up speed is also going up. And let's let the position at time 0 equal, I don't know, maybe you start out at 3 meters. And let me add some units here. This would be meters per second. And maybe your velocity at time 0 is, maybe you were headed to the left at -1 meter per second. So when the clock started, you were to the right of the origin, if the origin's here, and you were moving that way with this speed. And suppose we'd like to find the position now at t equals 5 seconds. Where the heck is this particle or vehicle going to be when the clock says 5 seconds? You cannot answer this question by making reference to this equation. Maybe you're thinking, well, that's easy. You just plug in numbers, right? Plug in 5 seconds for t, plug in the initial velocity of -1, plug in the position of 3 meters, and plug and chug in the calculator. That's not going to work because this equation is only applicable for constant, constant acceleration. It's a constant acceleration kinematic equation. So we need to start from scratch, go back to the drawing board, go back to square one, start all over again, revamp, get our bearings, and repeat the procedure that I demonstrated. So we'll start with recognizing that the time derivative of velocity is acceleration. Same starting point, because this is always true, right? Acceleration is always, by definition, the time derivative of velocity. So then I'll put my dt next to the a, and I'm being careful to leave some space here so I can draw my worm. And just like before, I'm going to use my initial time as 0, and my final time is what I'll just call t. Now, the reason I'm doing this, notice how the initial conditions, the position and velocity were specified at time 0. That's why I can do this. If the position and velocity were specified for some other time, I would have to do this differently. So I guess what that means is if I put this on a test, if I ask you to calculate the position for non-constant acceleration, I'll do it this way so that you can choose the limits the way I'm choosing them. Okay, the velocity limits would be v initial, and the final velocity is just v. So this is the velocity at that time. This is the velocity at time 0, which is why I'm calling it t naught. Okay, well, let's now plug in the acceleration. I can't just pull the a out because it's not a constant now. The acceleration depends on time. So I'm really integrating 2t with respect to t, from 0 to t. I can pull the 2 out because that's the constant. What's the antiderivative of t? Raise the power from 1 to 2, so t squared, divide by that new power, t squared over 2. Well, that 1 over 2 would cancel the 2 that's already there. So it's just t squared, upper and lower limits, it just comes out to be t squared. Well, don't forget about the first part, right? So this says v minus v naught equals t squared. And we can write that as the velocity at any time. This is some variable velocity at time t, would just be the initial velocity plus t squared. Great. Now we know how the velocity depends on time. We can integrate once more to find how the position depends on time, because that's what we're being asked for. What is the position at 5 seconds? If the problem we're asking what's the velocity at 5 seconds, we know how the velocity depends on time already because we've done that first integral. I could just plug in the 5 seconds and plug in my initial velocity of -1, and I would be done with it. Maybe I should emphasize let t naught equal 0 seconds. We know what the velocity is at 0 seconds. This really means the velocity at 0 seconds. And since I'm labeling 0, I'm giving 0 seconds the label t naught. That's why I chose the corresponding notation v naught. V naught is the velocity at time t naught, which is 0. Okay. Now, for the next integral, we remember that the time derivative of position is velocity. Let me move the dt to the other side and say dx equals v dt. And you'll probably make better use of your paper when you're doing this. I'm killing a lot of trees here, but that's because I guess I'm presenting. Let's integrate both sides. We're integrating from t equals 0 to some final time t, and the corresponding initial position should be called x naught, and the final position would just be called x, so this is the position at that final time t. I'll go ahead and do this integral, so x minus x naught is what I get. And I can't just pull v out because it's not a constant. In fact, here's how it depends on time. So I'm really integrating this function of time with respect to time. I've moved the x naught to the other side, and I think you can all do this integral in your heads. The integral of v naught, which is a constant, is just v naught t. Here we would have to raise the power of 2 to a power of 3, divide by that new power, so it's 1/3 t cubed from 0 to t. And like I said, if you're integrating a polynomial, you'll get another polynomial where the lowest power is t to the first power. That means when you plug in your lower limit of integration, it just goes away. And here we are. The position at any time is the initial position plus the initial velocity times time plus 1/3 t cubed. This is not the same as the more familiar equation that you've been doing or using for constant acceleration kinematics. Yes, you have an x naught in both instances. And this looks the same. That's actually a plus. Wait a minute. No, they are the same. Yeah, the first two terms evidently are the same. Okay. Have I missed something? I believe I did this correctly. So, I don't know if that's true in general. I wouldn't quote that as a general rule that the first two terms look the same. In fact, I suspect I did something wrong here. And the worst part about that, it's not the fact that I've confused you. Yeah, that's a bummer, but it's that I have to go back and fix this video. When I integrated the acceleration, no, I think I did it. I think I did that okay. Or did that correctly? Okay. So the difference then is in this last term involving the acceleration. If the acceleration was constant, we got a t squared as our highest power. In this instance, the acceleration was not constant. In fact, it's no surprise. Look at the power of the acceleration. Where did that go when I first wrote this problem down? Wasn't it 2t? I specified that the acceleration, it's right here. The acceleration was proportional to t to the first power. Well, since we're integrating twice, that power should go up by 2. It's no surprise that the highest term is t to the third. All right, so the position at time 5, I could just write x of 5, or I could be really pedantic and say x at t equals 5 seconds would be, what's the initial position? I specified that it was 3, so we plug that in, plus an initial velocity of -1. -1 times 5 seconds plus 1/3 5 cubed. Do you really want me to do that with the calculator? I don't have one handy. Can we do this in our heads, or can I do it in my head? 5 squared is 25. I know 5 times 5 again is 125. 125 over 3. Okay, so this is a fraction. You can just punch that into your calculator. If you saw something like this on an exam, is it super important to get that last number correctly? I would say no. If you want full credit, let's say it's a 20-point problem. To get those 20 points, I am looking for the correct number at the very end. But if you did all the correct work, and I can see that you understand how to integrate correctly, you understand what to do when the acceleration is not constant, that's the majority of the credit. Maybe I take off 1 or 2 points for flubbing everything with the calculator at the end. But most of the work has been done, okay? So maybe get some practice with 1 or 2 non-constant acceleration problems. You can experiment. You know, I chose this, the simplest thing I could think of that wasn't actually a constant, just 2t. See if you can do it when the acceleration is t squared or even t cubed. In each case, you're just integrating as you would in a calculus class. You could use the power rule. The only other thing I could throw at you really would be like a trig function, something easy to integrate. This is not a class about techniques of integration, so I'm not going to choose an acceleration where you have to use a table of integrals, or trig substitutions, or u substitutions, or integration by parts, or you have to consult Gradstein and Resnick. You don't know what I'm talking about. Okay, in the subsequent video, I'll go back and do a few more homework problems using the concepts developed in this video.